So let us look at some common faults that we can detect using the vibration technology or vibration analysis technology. So the first fault that we can detect using this vibration analysis technology is unbalance. So we are going to look at what an unbalance is and how we can identify unbalanced condition, okay, in the equipment. So like we said earlier, unbalance is a one-time RPM event. So when you look at the spectrum, because as you hover in your analysis software, as you hover through all of this peak, it will tell you the order, okay, at which this frequency is happening. So if it is 1, that is most likely an indication that you have an unbalance within the system. So misalignment too, like we said earlier, is a 2 times RPM event. So if you look at all of this peak, okay, the one that is significant among them, as you look at them, it will show you the order. So if it is 2 times RPM, okay, that will tell you that it is misalignment. So because misalignment, we will get it in 2 times information about misalignment, okay, that fourth condition, we will get it at 2 times RPM. Remember, we said if we are confused, we are not too clear as to the fourth condition that is causing that significant peak, we can carry out the phase analysis, okay, to determine if it is actually misalignment. So in the phase analysis, we use multiple channel analyzer, take ASIA reading of both end of the shaft, the inboard of both equipment, the driver and the driven, okay, take the ASIA reading. If it is 180-degree out of phase, remember we said they are supposed to be in phase because of the fact that both shaft has become one by virtue of the coupling. So if they are out of phase because of the axial movement caused by the misalignment, then we have misalignment condition. So bearing defects, like we said earlier, you get them within the bearing range, which is around the ball pass frequency range, okay, the number of balls that you have in the bearing times the speed of your equipment. Then resonance too, we can use vibration to detect resonance, and of course gearbox problems. So let's look at them in a little detail, okay. So this is the gearbox that we're talking about. So you see the speed of rotation times the number of teeth that you have on this gear will give the gear mesh frequency. So like we said, we'll look at them in a little bit detail. So the unbalance. What is unbalance? Unbalance is when the center of mass of that rotor, okay, does not coincide with the center of gravity of the rotor. So if it does not coincide with the center of gravity, the center of mass and the center of gravity does not coincide, they see that the rotor will tend to be thrown as it's rotating towards the center of mass. Are we getting it? And thereby causing that one-time impact or one-time vibration force or one-time vibration event, okay, that will be captured by your vibration analyzer when you go out to conduct your vibration. That is when you go out to collect your vibration data. So unbalance like that, like we said earlier, you will see them most likely at the one-time RPM event, and that's what you are seeing on your screen. This is the spectrum. So unbalance typically appears at the turning speed of the machine, center of mass not at the center of rotation, which is the center of gravity, okay. So we can also have unbalance on fans too. It's the same thing. The center of mass will not coincide with the center of rotation. So you'll be having that throwing force each time the rotor rotates to that position of unbalance. So you see the event repeating itself every one time RPM or one time turning speed. So for this overhung fan, you see the effects of the unbalance. Okay, so that unbalance is still a one time RPM event. So if you have multiple unbalance as you have here, the summation of all of the unbalance, once you resolve those forces, they'll be acting at a particular direction also. So you also have the one time RPM events. Okay. So misalignment, like we have said before, misalignment is when the center line of the driver, okay, shaft, the center line of the driver shaft does not coincide with the central line of the driven shaft. So if the equipment is properly aligned, you see that both center lines will coincide. So once they do not coincide, we have misalignment. And as we have acknowledged earlier, as we have seen earlier, the misalignment could either be angular, okay, or offset. So, but in real life, you have a combination of both of them. So which means that that misalignment force must be overcome as the equipment is turning, and that will exert some degree of pressure, okay, on the bearing, and that force will be picked up by your vibration sensor or accelerometer. So at that instance, you'll see that most of the misalignment problems, you'll see them either in your one time or two time turning speed. Okay, so remember we said unbalance, you will see them in one time RPM or one time turning speed. So if there are confusion as to what is actually causing the unbalance, then you can do your phase analysis. Okay, so do your phase analysis as we have explained earlier, then you'll be able to confirm that yes, this is a misalignment when it is 180 degrees, when both signals are 180 degrees out of phase. Then fourth, with your bearing. Okay, this rolling element bearing, these are the balls. So in this now we have 1, 2, 3, 4, 5, 6, 7, 8 balls. Okay, which means that faults on this bearing, we will see them at that bearing frequency range, which is 8 times the turning speed from this bearing, because we have 8 balls, 8 times the turning speed of the equipment. So that is the area we will get the bearing defect. So bearing wear shows up at specific peak related to the geometry of the bearing, as we have acknowledged. So which means that, like in this case now, we will get information about this bearing around this area, okay, which is about the 8 times the turning speed. Okay, so that is where we will get it. Then as for this bearing that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, which means around this area we'll get information about the bearing. So if there are any fault condition in the bearing, okay, it will show up around this area. You see peaks around this area. Are we getting it? High vibration in this area, that will tell you that such fault condition is coming clearly from the bearing. Then we also have a resonance condition. Okay, resonance is when the frequency of vibration coincides with the natural frequency of the equipment. Are we getting it? So that tends to amplify the vibration. So if you see that abnormal peak, most likely you may be looking at resonance, okay, at that resonance frequency. So vibration frequency is equal to the natural frequency of the machine. Then you see that excessive vibration amplitude, okay. And one of the major characteristics of that kind of peak is that it is narrow. You see the band that is very narrow. Are we getting it? So that will give you an indication that you are looking at resonance, okay. So resonance is not something that you just confirm straight from a single vibration information. So you have to test. Once you suspect resonance, you have to test further to see that what you have to confirm that what you're actually having is a resonance condition. So we have the startup or shutdown test that you can carry out. Okay. So from there, from that test, you record your baseline vibration information during your initial startup. Then, as the equipment is going through the startup phase, you should be able to identify the resonance frequency. Then you shut down. Then, as it's coasting down too, you also carry out your vibration. That is, you collect vibration information to be analyzed later. Then you repeat the process again to see if those significant events will repeat themselves at the same time. Okay, then you compare the results that you have to draw your conclusion. So what do you do during the startup test? The first step is to initiate startup of the equipment. Okay, then as you start up the equipment, you gradually increase the speed of the machine from that position of rest. Okay, but as you are doing that, you are collecting the vibration information from the machine and then recording the information that you are gathering. Then as you are doing that, you need to pay attention, very close attention, to any sudden peak or rise in vibration levels as the equipment is starting up. Are we getting it? Pay close attention to it and look at if there is any such. Look if it is narrow band and if the phase is erratic also. Then how do you identify that what you are looking at is a resonance frequency? Of course, you have to analyze the information using the frequency spectrum. Okay, then when you look at the frequency spectrum, like we said earlier, what you'll be looking at is that very sharp peak with narrow band. Okay, so they often indicate that what you are looking at most likely will be resonance. So you now compare what you have identified with the machine operating speed. Then you repeat the shutdown. That is, you repeat the process while you are shutting down that is, you collect the vibration information while you shut down. Okay, so you shut down the equipment, and as the equipment is coasting down, you collect the vibration information. So as the equipment speed is reducing, you collect the information, okay, to see how the vibration is coasting down. Then, and to also look if you see any form of peak as it's coasting down too. Then you repeat the process again to see if it will repeat itself at that particular time or position or point where you saw that peak earlier. So you now analyze the method, you compare results, okay, and then if there are frequencies of interest that you identify during the startup and shutdown, you compare them and verify that these frequencies they are consistent before you be able to conclude if it is resonance frequency that you are looking at. So another way of testing for resonance is the impact test. The impact test. So on the impact test, you select an impact hammer, okay? Then that is the machine will be in that will be shut down. Okay, will be in a state of shutdown. It will not be working at that instant. Then you attach a sensor, as you can see on the screen. You attach a sensor, then you connect that sensor to your vibration analyzer, then you perform the impact. Okay, so you also use multiple channel analyzer. The hammer will be attached, the impact hammer will be attached to one of the channel, okay, and then the sensor will be attached to the other channel. So as you as you hit the electric motor, okay, the impact information will be sent through the cable that is connected to the impact hammer, and then the sensor also will also pick up the impact, okay, and send to your analyzer. So this is an example of the response and the impact. This is the impact and this is the response. See as it's coasting down, okay? So you analyze that information to confirm that it is what you are looking at is resonance. So we have described this process before. So then you can now calculate the natural frequency of the structure base and identify the resonance frequency. Then you interpret the result, compare the measured natural frequency with the expected frequency of the machine, then assess the damping characteristics of the structure based on the shape and width of the resonance peak. Then identify any potential issue or concerns based on the results. So another common fault that you can detect again with vibration analysis is the gear problems or gear faults. So like we said earlier, you will see all of this in the gear mesh frequency, the number of teeth times the number of rotations. So just for you to go to that area and try to analyze the sideband to know what is actually happening within the gearbox. Okay.